I want to do an example to help you understand one major problem with the mean absolute deviation. Let's imagine that this is a population of 42 people, and that a researcher is interested in the amount of sleep that the members of this population are getting on average. In this population, there's one person who's getting 2 hours of sleep per night. There's 2 people who are getting 4 hours of sleep per night. There's 10 people who are getting 6 hours per night. There are 10 people who are getting 7 hours per night. There's 10 people who are getting 8 hours per night. There's 2 people getting 10 hours per night, and 1 person getting 12 hours per night. Let's start off with finding out what the mean hours of sleep is for this population. We can use Excel to calculate the mean of this population. This column is showing the sleep times of all 42 people in the population. To get the population mean, we could add the 42 numbers and divide the total by 42, but Excel can do the work for us. We just need to go down to the bottom of the column down here and find an empty box, and then we type in equals average. Excel uses the word average instead of mean, but average and mean mean the same thing. Then we make a left parentheses right there, and then we highlight the 42 numbers. And then we type in a right parentheses to close the formula, and then we press enter, and we get the population mean right here. The population mean is 7. So 7 is the number that we would have gotten if we had added the 42 numbers and divided the total by 42. So the mean hours of sleep that this population is getting per night is 7 hours. 7 hours is the population mean. So now we know that the population mean is 7 hours of sleep per night. These 42 people are getting 7 hours of sleep per night on average. So I'll put down here that the mean of the population is 7. We can see that the mean of the population is 7, but not everyone in the population is getting 7 hours of sleep per night. People are spread out in both directions, to the left and to the right. Some people are getting 6 hours. Some people are getting 4 hours. Some people are getting 8 or 9 hours. 8 or 10 hours. Some people are even getting 2 or 12 hours. So there's definitely some spread in this population. So how can we calculate a value to actually measure the amount of spread in this population? We could calculate a value called the mean absolute deviation, which is the average distance from each person to the mean. And we can go back in Excel to calculate the mean absolute deviation. The first step in getting the mean absolute deviation will be to subtract each value in the population by the population mean of 7. Here I'll type the word mean just to show you that every cell in this column will have the mean of 7. So this column will just have the mean of 7 all the way down. I can copy and paste to save some time. First, we have to subtract each value in the population, each sleep time, by the mean of 7. So we can do that by typing in equals, and then clicking right here on the first person's sleep time, and subtracting it by the mean of 7, and then pressing enter. So this person sleeps 2 hours per night, so this person's data value is 2. When we subtract this person's data value by the mean of 7, we get -5 as our answer. And when you subtract a data value by the mean, you get a number called a deviation. So this is our first deviation. We can just drag this down to get all of the other deviations. So every person in the population has his or her own deviation. People who were above the mean have positive deviations. People who are below the mean have negative deviations, and people who are at the mean have a deviation of 0. The next step is to get the absolute deviations. To get the absolute deviations, we just take the absolute value of each of these deviations, which pretty much just means that whenever there's a negative sign, we just leave it off. So all of these negative numbers here will just become positive numbers. To do this, we can type in equals ABS, that stands for absolute value, and then click on the parentheses and highlight the first deviation, and then close the parentheses and then press enter. So the absolute value of -5 is 5. And what the absolute value is just the distance from the person's data value to the mean. So I said that this person is sleeping 2 hours per night. So this person has a data value of 2. And the mean of the entire population is 7. So this person's data value is 5 away from the mean, which is why this person has an absolute deviation of 5. A person who has a data value that's 5 away from the mean will have an absolute deviation of 5, because the absolute deviation is just the distance from the person's data value to the mean. Here we have another person in the population who's sleeping 4 hours per night, and this person's data value is 3 away from the mean of 7, which means that this person will have an absolute deviation of 3. A person who has a data value that's 3 away from the mean has an absolute deviation of 3. So this second member of the population has a data value of 4, and this person has an absolute deviation of 3, just because this person's data value is 3 away from the mean. Here we have another member of the population who is sleeping 4 hours per night, and this person's data value is also 3 away from the mean, which means that this person will also have an absolute deviation of 3. The absolute deviation is just the distance from the person's data value to the mean. Here we have a person who's sleeping 6 hours per night, and this person's data value is 1 away from the mean of 7. Since it's 1 away from the mean of 7, this person has an absolute deviation of 1. The absolute deviation is just the distance from the person's data value to the mean. And we can get all of the absolute deviations by just dragging this down. So every member of the population has an absolute deviation, which is just the distance from that person's data value to the mean. All of these people who are getting 8 hours of sleep per night are all 1 above the mean of 7, which is why they all have absolute deviations of 1. These people who are getting 7 hours per night are 0 away from the mean of 7, which is why they all have absolute deviations of 0. This person who's sleeping 10 hours per night is 3 away from the mean of 7, so this person has an absolute deviation of 3. And this person who's sleeping 12 hours per night is 5 away from the mean of 7, so this person has an absolute deviation of 5. So all of these absolute deviations are just distances from the data value to the mean. And if we calculate the mean of all of these distances in here, we'll get the mean distance to the mean, or you could say the average distance to the mean. So let's get the mean of all of these numbers in the absolute deviation column. When we add up all of the absolute deviations and divide the total by 42, we get 1.09. So the average distance from a person's data value to the mean is 1.09. And this answer right here that I'm saying is the average distance to the mean. is called the mean absolute deviation. It gets that name because it's the mean of all of the numbers in the absolute deviation column. Right here we can see that the mean of the population is 7. So on average, the people in this population are getting 7 hours of sleep per night. And we can see that the mean absolute deviation is 1.095. That means that on average, each person is 1.09 away from the mean. The average distance to the mean is 1.095. And that makes sense because we can see right here we have 10 people who are 1 away from the mean. All of these people who are getting 6 hours of sleep are 1 away from the mean. Here we have 10 other people who are 1 away from the mean because they're all getting 8 hours of sleep. So we have 20 people who are 1 away from the mean because 10 plus 10 is 20. And these 10 people who are getting 7 hours of sleep are all 0 away from the mean. Here we have 2 people who are 3 below the mean, and we have 2 people who are 3 above the mean. And here we have 1 person who's 5 below and 1 person who's 5 above the mean. So there's 20 people who are 1 away from the mean. There's 10 people who are 0 away from the mean. There's 4 people who are 5 away from the mean. I'm sorry. There's 4 people who were 3 away from the mean. And there's 2 people who were 5 away from the mean. So all of the distances are, each person has a distance to the mean. So overall in this population there's 42 distances. 20 of those distances are 1, 10 of those distances are 0, 4 of those distances are 3, and 2 of those distances are 5. And the mean of all of those distances is 1.095. Because I said the mean absolute deviation is just the average distance to the mean. Now that we know what the population mean and the population mean absolute deviation are, let's say that a researcher comes along and is interested in the mean hours of sleep that this population is getting per night. But for some reason, the researcher can't calculate the population mean. Maybe the researcher doesn't have enough time to collect data from all members of the population. So since the researcher isn't able to collect data from all population members, what the researcher is going to do is select a sample of 5 people from the population and ask those 5 people how many hours of sleep they're getting per night. And then the researcher is going to calculate the mean of those 5 answers by adding them and dividing by 5. And then the researcher will have the sample mean. And the researcher is going to use the sample mean to estimate or to get a rough idea of what the population mean equals. And the researcher isn't just interested in the average amount of sleep this population is getting. The researcher is also interested in how much spread there is in the population. And what the researcher is going to do is calculate the mean absolute deviation of the 5 people in the sample to estimate or to get a rough idea of how much spread there is in the entire population. In other words, the researcher is going to calculate the mean absolute deviation of the sample to estimate the mean absolute deviation of the entire population. So what I've just said is that the researcher is going to calculate the mean of his or her sample to estimate the population mean, and the researcher is going to calculate the mean absolute deviation of his or her sample to estimate the mean absolute deviation of the entire population. Let's say that the researcher randomly selects a sample of 5 people from this population of 42 people, and the researcher uses those 5 people to calculate the sample mean and the sample mean absolute deviation. Now let's think about how likely it is that the mean of the researcher's sample of 5 people will do a good job of estimating the population mean, and how likely it is that the mean absolute deviation of the researcher's sample of 5 people will do a good job of estimating the population mean absolute deviation. To answer that question, we need to look at what would be likely to happen if several different samples of 5 people were randomly selected from this population, and the mean and mean absolute deviation were calculated with each of those samples. I actually randomly selected several different samples of 5 people from this population, and with each of my samples I calculated the mean and the mean absolute deviation. Let's start by looking at the mean of each of my samples. The first sample that I got was this sample of 5 people right here. I randomly selected this sample of 5 people, and in this sample there's 3 people who are getting 6 hours of sleep. There's 1 person who's getting 7 hours of sleep, and 1 person who's getting 8 hours of sleep. So this would be the sample right here, and this would be the data set that I would record from the sample, because I would ask all 5 people in my sample how many hours of sleep they're getting per night, and I would record their 5 answers. So this is person 1, person 2, person 3, person 4, and person 5. Let's look at what the mean of my sample is. After I added these 5 numbers and divided the total by 5, I got a sample mean of 6.6. So the mean hours of sleep that these 5 people are getting per night is 6.6. So my first sample mean is pretty close to the population mean of 7. It's pretty close to the number that I would get by adding all 42 numbers and dividing the total by 42. It's a little bit lower than the population mean, but not much. So next I randomly selected a different sample of 5 people, and the second time I ended up getting this sample. I ended up getting 2 people who were getting 7 hours of sleep, 2 people who were getting 8 hours of sleep, and 1 person who's getting 10 hours of sleep. You can see that sample right here. And these are the 5 answers that I recorded from my sample. These are just the hours of sleep that the 5 people in this sample are getting per night. And when I added their 5 answers and divided the total by 5, I got a sample mean of 8. So this sample is 1 above the population mean of 7. So this sample mean was a little bit more accurate than this sample mean, because this one underestimated the population mean by 0.4, and this one overestimated by 1 whole hour of sleep. And next I randomly selected a third sample of 5 people, and I ended up getting this sample right here. I ended up getting 1 person with 4 hours of sleep, 1 person with 10 hours, 1 person with 6 hours, and 2 people with 8 hours. You can see that sample right here, and this is the data that I recorded from that sample. These are the 5 sleep times of the 5 people in the sample, and the sample mean is 7.2. So if I added these 5 numbers and divided the total by 5, I would get 7.2. So you might imagine that I'm a researcher who's studying this population of 42 people, and I'm selecting a sample of 5 people over and over again. I'm selecting different samples of 5 people over and over again, and each time I'm calculating the sample mean. So the next time I randomly selected a sample of 5 people, I ended up getting these 5 numbers right here. I ended up getting these 5 people. I ended up with 2 6s, 2 8s, and 1 7. And the mean of this sample is 7. Actually, this sample mean is equal to the population mean. So this one actually perfectly estimates the population mean. If you're wondering how I randomly selected these samples, I used Excel to randomly select 5 numbers out of the 42, and I just did that over and over again. This was the next sample of 5 people that I ended up getting. I ended up getting 2 6s, 2 7s, and 1 8, which would be this sample right here. And the mean of this sample is 6.8. If you added these 5 numbers and divided by 5, you would get 6.8. So this one estimates the population mean pretty well. It's only 0.2 away from the population mean. The next sample of 5 people that I ended up getting was this one right here, with a sample mean of 7, which is equal to the population mean. I selected another sample of 5 people, and I got these 5 numbers. I ended up getting two 6s, 2 7s, and an 8. So these are the 5 numbers in this sample, and the sample mean is 6.8. This was my last sample of 5 people. I ended up getting 3 6s, a 7, and an 8. And this time the sample mean was 6.6. So each sample has its own sample mean. Some of them were more accurate than others because some of them were closer to the population mean and some were further away from the population mean. Some of them overestimated the population mean. Let's look at which ones overestimated. 8 is higher than the population mean of 7, so this sample overestimated the population mean. 7.2 was a little bit above 7, so this sample overestimated the population mean. So 2 of them overestimated. How many of them underestimated? 6.6 is lower than 7, so this sample underestimated the population mean. 6.8 is also lower than 7. This 6.8 is lower than 7, and 6.6 is lower than 7, so 4 out of the 8 samples underestimated the population mean, and 2 of the samples estimated the population mean perfectly because 2 of the samples had a sample mean of 7. So now let's look at each of these sample means on a graph down here. Let's make a graph of the sample means. You can see right here that the population mean is 7. This is the mean of all 42 population members. And these are the sample means. These are the means of the 8 samples. We had 2 sample means of 6.6 right here. We had 2 sample means of 6.8. Those are these 2 x's right here. We had 2 sample means of 7, which are these 2 right here. We had 1 sample mean of 7.2, which is right here, and 1 sample mean of 8, which is this x out here. So these are just the 8 sample means that we have calculated here. And we can see that overall the sample means are pretty close to the population mean. The sample means fall between 6.5 and 8. So overall, the sample means did fall pretty close to the population mean of 7. So if a researcher takes a random sample of 5 people from this population and calculates the sample mean, the researcher can be pretty confident that the sample mean will be close to the population mean because we can see that over time the sample means tend to be close to the population mean. Now let's look at the mean absolute deviation of each of the samples. Let's look at what happens when you use the sample mean absolute deviation to estimate the population mean absolute deviation. Let's start by looking at the mean absolute deviation of my first sample. To get the mean absolute deviation of this sample, we would subtract each of these data values in the sample by the sample mean of 6.6. We would get our deviations, and then we would take off all of the negative signs to get absolute deviations. And then we would add the 5 absolute deviations and divide the total by 5. And then we would get the mean absolute deviation of the sample. The mean absolute deviation of this sample is 0.72. And what that means is that inside this sample of 5 people, the average distance to the mean of 6.6 is 0.72. On average, these 5 numbers are 0.72 away from the mean of 6.6. And we can see that the sample mean absolute deviation underestimates the population mean absolute deviation. Let's look at the mean absolute deviation of the second sample. This time we subtract the 5 data values by the sample mean of 8, and we get our deviations. And then if we leave off the negative signs, we get absolute deviations. Then to get the mean absolute deviation, we just add the 5 absolute deviations and divide the total by 5, because the mean absolute deviation is just the mean of the absolute deviations. And it comes out to 0.8, because these numbers add up to 4. 1 plus 1 plus 0 plus 0 plus 2 is 4, and 4 divided by 5 is 0.8. So inside this sample of 5 people, the average distance to the mean is a distance of 0.8. And we can see that this sample mean absolute deviation also underestimates the population mean absolute deviation. Now let's look at the mean absolute deviation of the third sample. You might be able to guess that the mean absolute deviation of this sample will be higher than the mean absolute deviation of these samples. Because notice how this sample of 5 people doesn't have very much spread to it. Because these 5 people are all between 6 and 8. We have 3 6s, a 7, and an 8. And since these 5 people are pretty close together, they don't have a very high mean absolute deviation. These 5 people are also pretty close together. We have 2 7s, 2 8s, and a 10. So they also have a pretty small mean absolute deviation. This mean absolute deviation is a little bit higher than this one because this sample does have a little bit more spread than this one does. This person with a 10 is adding a little bit more spread to the sample. But this sample right here has even more spread than these samples do, because here we have some people who were spread out between 4 and 10. We have a 4, a 6, 2 8s, and a 10. So this sample has more spread than these two samples do. So this mean absolute deviation should come out higher than these mean absolute deviations. And the mean absolute, well, after we do the math, the mean absolute deviation comes out to 1.76, which is quite a bit bigger than the mean absolute deviations of these samples. So overall, when a sample has more spread, the mean absolute deviation of the sample is higher. When a sample has less spread, the mean absolute deviation of the sample is lower. You can probably guess that this sample right here will have a lower mean absolute deviation, similar to this sample right here, because these 5 people aren't very spread out. So it's 0.8, just like the sample over here. So far, 3 of the samples have had a mean absolute deviation that's underestimated the population mean absolute deviation, and 1 sample has had a mean absolute deviation that's overestimated the population mean absolute deviation. Let's look at the next sample. This one is 0.64, and which means that it's similar to these mean absolute deviations up here. So notice so far how 4 of the samples have had pretty low spread. Sample 1, sample 2, sample 4, and sample 5 have had pretty low spread, so they've had lower mean absolute deviations. Sample 3 has had the most spread, so it's had the highest mean absolute deviation. I'm just trying to remind you of how the mean absolute deviation goes up when there's more spread. What about the next sample? Well, this sample has quite a bit of spread to it, just like this sample up here, because we have the 4 and the 10. So this mean absolute deviation is a 1.6. This should actually say sample 7, but I said 6 by accident. This one will have a lower mean absolute deviation because these 5 people are pretty similar to each other. They're all getting somewhere between 6 and 8 hours of sleep. This one comes out to 0.64. This one should be about the same. It's 0.72. So let's look at how many samples have overestimated the population mean absolute deviation. Well, 1.76 is higher than 1.095, so this overestimates. 1.6 is higher than 1.095, so this overestimates. Now let's look at how many samples have underestimated the population mean absolute deviation. Well, sample 1 is a 0.72. That's lower than 1.095. 0.8 is lower than 1.095. So these two both underestimate. 0.8 is lower than 1.095, so this one also underestimates. 0.64 is lower than 1.095, so sample 5 also underestimates the population mean absolute deviation. 0.64 is lower than 1.095 once again, so this sample, which should be sample 7, underestimates the population mean absolute deviation. Sample 8 has a mean absolute deviation of 0.72, and that's lower than 1.095. So sample 8 underestimates the population mean absolute deviation. So 0.72, 0.8, 0.8, 0.64, 0.64, and 0.72 are all lower than 1.095. So all of these 8 samples, all of these 1, 2, 3, 4, 5, 6 samples underestimate the population mean absolute deviation. So we've seen that 2 out of the 8 samples overestimate the population mean absolute deviation, and 6 out of the 8 samples underestimate the population mean absolute deviation. We can see that right here if we make another graph of sample mean absolute deviations. Each sample mean absolute deviation will be an x, so we'll have 8 x's right here. The population mean absolute deviation was about 1, so if we round it to 1, we'll say that it's about right here. These 6 x's are the samples that underestimated the population mean absolute deviation. We have 2.64s, which are right here. We have 2.72s, which are right here. And we have 2.8s, which are right here. These are the 6 samples that underestimated. These are the 2 samples that overestimated. This was the sample that had a mean absolute deviation of 1.6. That's 1.6. This right here is a sample that had a mean absolute deviation of 1.76. So if we compare these 2 graphs, we can see that over time, the sample mean underestimates the population mean about the same that it overestimates the population mean. Meaning over time, the amount of underestimation that happens is about equal to the amount of overestimation that happens. But we can see with the sample mean absolute deviation, that's not true. The sample mean absolute deviation has a stronger tendency to underestimate. It underestimates more often than it overestimates. So we can see right here, sample means tend to underestimate and overestimate the population mean to an equal extent. If we kept on doing this with more and more samples, we would see that this side that's lower than 0.7 would have about the same number of x's as this side that's above 7. So the number of x's that would be in the underestimating area would be about equal to the number of x's in the overestimating area. But the sample mean absolute deviation has a tendency to underestimate the population mean absolute deviation. So if we kept on doing this with more and more samples, if we kept on taking more and more samples of 5 people and calculating the mean absolute deviation each time, we would continue to have more x's piling up in this underestimating area down here, and we would have fewer x's piling up here in the overestimating area. So we can see that we have one type of value that tends to underestimate and overestimate equally over time, and we have one value that tends to underestimate more than it overestimates over time. A value that underestimates and overestimates equally over time is called an unbiased statistic. The sample mean is an unbiased statistic because it tends to underestimate and overestimate equally over time. It's not biased toward underestimation or biased toward overestimation, since it does both of them about equally over time. If we continued to select more samples and calculate more sample means, the sample means that would pile up on the underestimation side would be about equal to the number of sample means that would pile up on the overestimation side. The sample mean absolute deviation actually isn't an unbiased statistic. It's a biased statistic. A biased statistic is a value that doesn't underestimate and overestimate equally over time. A biased statistic either underestimates more than it overestimates, or overestimates more than it underestimates. So the sample mean absolute deviation is a biased statistic because it tends to underestimate more than it overestimates over time. Now, why does the sample mean absolute deviation have a tendency to underestimate the population mean absolute deviation? Why is it a biased statistic in that way? Well, the reason is because samples tend to have less spread than the populations that they come from. We can see here that the population numbers are spread out between 2 and 12 in this curve right here. But we can see that a lot of these samples are coming from the middle area where a lot of people are, and a lot of the samples are either getting none of the people at the extreme ends of sleep, or a lot of the samples are getting not enough people at the extreme ends. For example, this sample has 4 people from the middle and only 1 person from the extremes, which is why its mean absolute deviation is lower than the population mean absolute deviation. So this sample has less spread than the population it comes from. So the sample mean absolute deviation is lower than the population mean absolute deviation. This sample of 5 people definitely has less spread than the entire population it comes from, because these 5 people are all between 6 and 8, and the population is spread out all the way from 2 up to 12, which is why this sample mean absolute deviation is lower than the population mean absolute deviation. Now, why is it a problem if the sample mean absolute deviation tends to underestimate the population mean absolute deviation? The reason is because the sample can give you misleading information about how spread out the population actually is. This sample is making it look like the population has less spread than it actually does. Because when you take a sample of 5 people, and the 5 people all fall between 6 and 8, and the mean absolute deviation of the sample is low, that seems to suggest that the population doesn't have very much spread and that all people are getting about similar amounts of sleep. That's actually not true. The population actually has more spread to it than the sample suggests. So it's actually better to use a different value than the mean absolute deviation to measure the spread of the data, because there's other values that actually give you more accurate information about how much spread there actually is in the population. There's actually values out there to measure spread that actually fairly accurately estimate the amount of spread that exists across the entire population. And those two values are called the variance and standard deviation. And we'll get into those values in the next video. In the next video, I'll go back to my old example where I had a population of 5 people and a sample of 3 people. And I'll show you how to calculate the variance and standard deviation of both the population and the sample. And we'll see that when those two values are calculated with the sample, there's actually an adjustment that's done to the formula to actually help avoid this tendency for the sample value to underestimate the population value.